Hello and welcome. We're ATOMBOTIX, your one-stop robot building partner. In this session, we'll go step by step through the 3D Ranger LiDAR, covering its specifications, scanning characteristics, and system architecture. Let me start with a quick overview of the key specifications of the 3D Ranger. It uses a 905 nanometer laser. With a 10% reflectivity target, the range goes up to 40 meters. So this product is positioned as a short-range LiDAR. The minimum range is 0.1 meters. For the field of view, horizontally we have a full 360 degrees, and vertically it spans from 7 degrees to plus 52 degrees, giving a total vertical FOV of about 59 degrees. The ranging accuracy is around 2 to 3 centimeters, which is well suited for perception and mapping tasks in AGV and robotics scenarios. The point density is 200,000 points per second, and the frame rate is 10 hertzes. So that's a quick baseline for the device just to set the stage. Now let's take a look at the FOV layout. Horizontally, the sensor rotates a full 360 degrees. Vertically, it covers from 7 degrees below the horizontal plane to plus 52 degrees above, forming the main detection region. The area above the upper boundary is essentially a blind zone outside the vertical FOV. Overall, the FOV shape is somewhat like a funnel, with coverage narrowing slightly at the top. On this page, I want to point out how the effective detection range varies across vertical angles. At smaller vertical angles, closer to the horizontal plane, the LiDAR achieves a longer effective range. As the beam moves upward toward the top of the FOV, the effective range gradually decreases. This variation is a natural result of the optical design and scanning geometry, and it's important to keep in mind for installation height and mapping coverage planning. Now let's move on to the point cloud characteristics, which are one of the unique features of this LiDAR. Unlike most conventional LiDARs where each scan frame repeats the same beam pattern, the 3D Ranger uses a non-repetitive scanning approach. Looking at the figure below, the horizontal axis represents integration time. The vertical axis shows the percentage of FOV coverage. The dashed lines show conventional LiDARs, 16 line, 32 line, 64 line. After one rotation, the coverage stabilizes, meaning points in certain directions won't get captured in subsequent frames unless the sensor or target moves. The solid line represents the 3D Ranger. As you can see, coverage increases over time. For example, after 0.5 seconds, the effective point cloud density can already surpass a 64-line LiDAR. How does it work? The LiDAR has 2 rotating prisms inside, each moving at slightly different speeds. This creates a slightly different beam pattern each frame, gradually filling in gaps from previous scans. Over time, point density increases, resulting in higher effective resolution. On the right, an example from a 2020 paper shows how the point cloud develops over 0.2 seconds, 1 second, and 40 seconds. This is an important feature to consider in applications like mapping, obstacle detection, or AGV navigation, where accumulated point density matters. Page 5 illustrates the system structure and optical path of the 3D Ranger. Let's start with the left diagram, showing the main components. The sensor is divided into lower and upper sections. A plus B at the bottom are the stacked PCBs, the main board on the bottom, and the motor control board on top. We'll see these clearly when the device is opened. Above them is a transceiver module, housing the laser diodes and the receiver. On top is the scanning module, including the motors and rotating prisms. The aviation connector is located on the right side. On the right diagram, the optical path works like this. 1. 4 laser diodes fire into a cylindrical lens for fast axis collimation. 2. The beam enters a trapezoidal prism, reflecting internally several times before exiting from the center. 3. A slow axis collimation lens then shapes the beam. 4. It passes through a wedge prism, which shifts the beam angle. 5. Finally, the beam reaches a right angle prism and is emitted into the environment. The returning light travels along a coaxial path. It enters through the right angle prism, then the wedge prism, portions of the reflected beam diverge and pass through side regions, eventually reaching the receiver. The scanning module contains two separate motors. The right angle prism handles horizontal 360-degree scanning. The linear prism adjusts the vertical scanning angle. Because the prisms rotate at different speeds, each frame hits slightly different points, creating the non-repetitive scanning pattern we discussed earlier. And that's the overall structure and working principle of the 3D Ranger LiDAR. Now let's move into the second section, where we'll take a closer look at the hardware itself. When we get to the live teardown later, some of the details won't be as clear as what we can capture in still images. So I'll walk you through the internal photos first to give you a more intuitive understanding of the internal structure. Let's start with this one, the main control board at the very bottom of the unit. You can see the core processor here, a Xilinx Zinc 7000 SoC, model XC7Z020 in the RPJ package. Right next to it is a 1GB DDR3 memory chip, along with a NOR flash device. Down on the lower right, you'll find two DAC chips, and on the lower left, there's an IMU that provides inertial measurement data. The back side of the board is simpler, mainly two oscillators and not many additional components. In the overall stack, this main board is positioned at the very bottom. When we open the unit later, you'll see that the SoC is mounted facing downward, with a thermal pad transferring heat directly to the metal base. Since this SoC is the highest power device in the system, placing it at the bottom helps the heat dissipate more efficiently. So that gives you the basic layout of the main control board. Next, let's look at this upper section, the motor control board. This name is something I assigned based on the PCB layout, which really does appear to focus on motor-related functions. For example, the motor control MCU here is a chip from Xuanzi. There's also a magnetic sensor, most likely used for reading the rotary encoder signals. This is the PHY chip for communication, and here you can see the DC-DC power components. This area right here will make more sense when we look at the teardown. It's basically a piece of insulating foam or fabric that creates spacing with no components underneath. It seems to serve mainly as structural support. Here we're looking at the next module above that, the transmit-receive module. At the top of the assembly, there's the lens, and underneath we have two stacked PCBs. On the right is a diagram showing the principle of the optical structure. You can see the laser marked in red, the wedge prism, and the lens element above it. The module can roughly be divided into three parts. The PCB with the laser emitter, which is the round board with the hole in the center, the receiver PCB below it, and the black center section, which houses the optical components and sits between the two PCBs. All together, it forms a kind of sandwich structure, with the optics enclosed in the middle. Now let's break down these components one by one. The first one is the optical bracket, which is the middle structure we saw earlier. This piece holds the lenses and the wedge prism inside, and the two PCBs are attached above and below it. The picture here shows the bracket after removing the PCBs. They're bonded with adhesive, but with heat, you can separate them and lift the PCBs off. Once removed, you can clearly see the internal lens, and although the photo is a bit hard to read, the wedge prism is also located inside this assembly. This is the laser emitter PCB. The shielding can has already been removed, so we're looking directly at the internals. The yellow region here is the laser diode. It appears to be composed of 4 EEL emitters. The laser output travels from this area into the central optical path through the components we discussed earlier. You can also spot the bonding wires leading out of the die, and these purple components should be the FETs used to drive and control the laser current. The photo isn't very sharp. I'll try to capture a clearer close-up later using a magnifier. This is the receiver PCB. The sensing element is in the middle section on the left. On the right is the backside with the shielding removed. Inside, there are 4 transimpedance amplifiers, likely TI's LMH 32401, which convert the photodiode current into voltage. As for the detector itself, whether it's an APD or a SiPM, it hasn't been opened here. So I can't confirm that based on this teardown. Now let's move on to the scanning module, which sits at the very top of the device, just above the emitter and receiver assemblies. After removing it from the main assembly, the module looks like this, It's essentially made up of two main parts. The optical section on top, including the right angle prism and the wedge prism, and the motor assembly underneath. You can also see the motor coil wrapped around the outside. On the right, there's a cross-section drawing that someone created, and I think it illustrates the internal layout quite well. It shows the two motors very clearly. The inner motor drives the rotating wedge prism, and the outer motor controls the rotation of the right angle prism for the full 360-degree horizontal sweep. The diagram isn't perfectly accurate in every detail. For example, the wedge prism's actual orientation is a bit different. In the real hardware, the horizontal reference edge is on the lower side and the top surface is tilted upward. But overall, the diagram still gives a good representation of the structure. You can also see the encoder discs here, two of them, along with a small PCBA in the middle. That serves as the incremental encoder for tracking the motor angles. Oh, and during the discussion just now, someone mentioned that the tilt angle on the upper prism is actually around 52 degrees, not 45 degrees. So that's a helpful detail to note. That's the general layout of the scanning assembly. Here's a conceptual diagram illustrating the scanning principle. This figure comes from a community member, so take it as an interpretation rather than an official reference. Looking at the right side, the two angular velocities, omega-1 and omega-2, represent the speeds of the upper and lower mirrors, respectively. Because these speeds differ, the resulting scan trajectory produces the shape shown. This diagram assumes the lower mirror rotates faster. However, based on other teardown observations and the circularity in the actual scan pattern, it seems likely that the upper mirror may rotate faster, which matches the pattern shown on the left. Either way, these diagrams help visualize how the combined mirror motion creates the final scanning pattern. On the left, you can see the right angle prism and the wedge prism that we removed. And on the right, actually, the wedge prism is still inside the module. It hasn't been taken out yet, and you can see the small prism still sitting embedded in the housing. Lastly, these are the encoder discs and the embedded encoder PCB. This PCB is built directly into the encoder assembly, so removing it would require destroying the structure. These photos are from another engineer who took the teardown further than I did. I stopped before this point to avoid damaging the module, but these images still serve as a helpful reference for understanding how the encoder is integrated inside the system. Hi everyone, welcome to the final section. Let's take a look at the actual hardware teardown. First, a quick note. The camera I brought this time doesn't have zoom, so some of the finer details aren't very clear. We can mainly get a sense of the structure and assembly relationships. I've already removed all the screws inside to save time. Here's the overall shape and dimensions of the LiDAR. This spot here is the QR code area, which I've covered with tape. On the right is the aviation connector. First, after removing the 4 screws at the bottom, we can see the main control board. There's a thermal pad on top to assist with heat dissipation. And you can see this connector here. Of course, the board is also fixed with these 4 screws, which I've already removed in advance. This is the main control board at the bottom. The SoC is mostly on the bottom surface, and on the back side, there aren't many components. Moving up, we have the motor control board. This is it. Underneath this board is a support structure, mainly to protect the transmitter, receiver module below, now we can take out the transmit receive module. It has the lens on top, forming a sort of sandwich structure with the receiver PCB below. You can also see the shielding plate and the transimpedance amplifier inside. That's about it for the bottom section. We won't remove the aviation connector here, nothing special about it. And now the top structure opening, it takes quite a bit of force to unscrew. But yes, it can be unscrewed because the top assembly is held in place with this . Keep in mind, the cover has a sealing gasket and there are 2 protective plates. I've already removed the screws on top. Here is the scanning structure we mentioned earlier, which contains 2 motors. Let's take out the route. You can see this is the washer I mentioned, and there's actually another washer embedded in the groove below. Back to the scanning module, the top one can rotate with a motor, and there's also a motor below. These 2 motors drive the 2 mirrors to rotate, and both are brushless. The top and bottom assemblies are glued in place, so you'd need a heat gun to remove them, which could damage the internal structure. I didn't open it further. So that's basically the teardown. Finally, a few thoughts on the LiDAR itself. Looking inside, the design is quite compact and some of the engineering is clever. For example, the transmitter receiver optical path is different from what we've seen in traditional forward-facing LiDARs. It has some unique design choices. After today, I'll open any remaining accessible parts and take clearer photos of the internal components. I'll share those high-resolution images later so everyone can check them out. Stay tuned for those updates. Thanks.